All right, let's take a look at torsion. Okay, so if you have a shaft, you can find the maximum shear stress by taking the torque times basically your outer radius of the shaft over your polar moment of inertia. This can also be written as the torque over Zp, which is your polar section modulus. Okay. Now, if you want to find the torque at any distance, the shear stress at any distance, take the torque, times it by some arbitrary distance, okay, away from the center over your polar moment of inertia. All right. Now, for solid shafts, J equals pi over 2 c to the fourth, or in diameters, pi over 32 d to the fourth. Okay, and then Zp is pi over 16 d to the third. For a tubular shaft, J equals pi over 2 c naught to the fourth, c I to the fourth. Oops, sorry. Or this is pi over 32 times the outer diameter to the fourth minus the inner diameter to the fourth. And Zp is pi over 16 times the diameter times the outer diameter minus the inner diameter to the fourth. Okay? A lot of the times when we start dealing with shafts, we deal with motors. So the power, P, or I like to do W dot sometimes, is the torque times omega, where omega is your angular velocity in radians per second. This can also be written as T times N times 2 pi over 60, where N is your revolutions per minute and omega is radians per second. Okay, let's look at torque and radius. So say you have a motor, and here is a pulley, and it's attached to another pulley with a different radius via a belt, and this has a shaft. Okay, let's call this RA and RB. The torque at B is actually a function of the ratio of the radii times the torque of A. Okay, let's do a couple example problems. Oops. Right here. Okay, so let's look at this one first. So we have a shaft, and we're trying to find the shear stress developed at 2 points. Okay, let me zoom in here. A, which is on the outside radius. Okay, let me do red. And then some distance away, B, which is out here. Okay. So we're looking for the shear stress. Now we want to find the torque. So the way I do this is you can look at it two ways. We're looking at this plane right here. Okay. So we can look at everything to the left of it. So we can cut the 12.5 on the right out. Okay. Or you can just look on the right, and it has to equal 12.5. Okay. But let's say we only looked at the left. All right, I'm going to draw here, and then this is where A is. So you have 30, and then you have 42.5. So if you sum the moments along the x-axis, you get 42.5 minus 30. Okay, assuming that way, we're assuming this way is positive, minus the torque, okay, we're assuming the torque is this way, okay, we get 0. So the torque has to be 12.5 kip per inch, okay. Okay, now let's look at the shear stress. Let's do A and B. So at A, it's the max because it's on the outer. Okay. So tau equals TC over J. So tau max at A, this would be the torque times basically your radius, which was what? Did it say the radius? Yes, 1.5 inch diameter. Okay, so 1.5 inch divided by 2 over J. And we know this is pi over 32 times the diameter, 1.5 inch raised to the 4th. Right? Let's double check. Torsion notes. Solid. Pi over 32 to the 4th. Pi over 32 to the 4th. Perfect. Okay, so let me plug this in. The torque was what? 12.5 kip per inch times 0.75 inches over pi over 32 times 1.5 inches to the 4th. Plug that in our calculator. And we get tau of A is 18.9 KSI. All right, now let's look at B. So tau of B is the torque times an arbitrary distance over J. So tau B, torque 12.5 kip per inch times, and this distance, 0.15 inches over pi over 32 times 1.5 inches to the 4th, and plug this in our calculator, and we get 3.8 KSI. Okay, so this is a very quick example of torque on a shaft as these bearings, as it's holding by the bearings, and you got these located, these rotations located at different spots. So you got different torques at different spots. Okay, now let's look at this example. So we have a pipe, has an inner radius of 40 millimeters and an outer radius of 50. If its end is tightened against the support at A using the torque wrench, okay, determine the shear stress developed in the material at the inner and outer walls along the central portion of the pipe. All right, so I'm going to redraw the sketch. And we have 80 newtons here. We have 80 newtons here, and it's right there. Okay, so we got 200 millimeters, 300 millimeters, and then we have this shaft right here. Oh, I want to do that in red. And what we have is a torque going around this way, T. Okay, so right here I'm looking at this plane, which is basically right there. And this is your, let's do coordinate systems. Up and down is Z. Left and right would be X. And then this is Y. So we're going to sum the moments in the Y, set it equal to 0. Okay. This way is positive. So we have 80 newtons times 0.2 meters plus 80 newtons times 0.3 meters equals, oops, sorry. And then we have, sorry, minus the torque equals 0. So the torque equals 40 Newton meter. Okay. And then we need to find tau out, which would be T times CO over J. Tau times the outer radius, right? Which is what? Let's call RO over J. Now J is pi over 2. This would be the radius out to the fourth minus radius in to the fourth. So torque, let's go ahead and plug the numbers. 40 Newton meter over pi over 2 times 0.05 meters to the fourth minus 0.04 meters to the fourth. And your out shear, so tau out, 0.35 megapascals. Okay, and let's calculate, let's say, find tau out. Let's go ahead and find tau in. Tau in, I'm just going to switch to T times Ri over pi over 2. R naught to the fourth, Ri to the fourth. Sorry about that. 40 Newton times meter times 0.04 meters over pi over 2, 0.05 meters to the fourth minus 0.04 meters to the fourth. Your shear stress inner is 0.3 megapascals. Actually, let's do it consistent. 28 megapascals. Okay, that's your shear stress. All right, another example. Now let's look at this motor example. So you have a solid steel shaft, AB, is used to transmit 5 horsepower from the motor M to which is attached. If the shaft rotates at 175, I like to call this actually N, not omega, N. And the steel has an allowable shear stress of 14.5 KSI. Determine the required diameter. All right, sweet. All right, so let's do this. Given we have power, which is 5 horsepower, and we're going to convert that. So there's 550 foot-pound per second in 1 horsepower. So we get 207.50 foot-pound per second. N is 175 RPMs. Let's find omega, which is N times 2 pi over 60. So 175 times 2 pi over 60. And this becomes 18.33 radians per second. And then we have tau allow, which is 14.5 KSI. And I think that's it. So find D. All right, we have a sketch. Just for complete, I won't complete it here. Just to keep rolling on the video. And let's get right to the solution. So you'd have assumptions and sketch. But let's get right to the solution. Okay. So let's find torque. So P equals T times W. The torque is therefore P over W. So the power was 2750 foot-pounds per second divided by 18.33 radians per second. And the torque becomes 150 foot-pounds. Okay, and then we can find diameter, basically saying that tau equals TC over J. Okay, and we know that tau times C, and this is a solid shaft. So for a solid shaft, it's what? Pi over 2 C to the 4th, correct? So this is torque over pi over 2 C to the 3rd. We can solve for that C. All right, so let's do the math here. So we get 2, no, let's go, it would be tau times pi, right, over 2, we can do that, times C to the 3rd equals the torque. And let's say C to the 3rd, we got torque over tau times pi over 2. And then we're going to pretty much raise this, oh, not square root it. We're going to raise it to the 1/3. Okay, let me double check my math here. 2 pi, yep, perfect. And this would be what, the radius. Okay, so let's go ahead and plug our numbers. What did we say the torque was? 150 foot-pounds divided by the allowable tau, which we said was 14 KSI, so 14.5 KSI times 1,000 to get that into PSI times pi over 2, all raised to the 1/3. So let me plug this in my calculator. So 14.5 times 1,000 times 150. Nope. Double check again. Oh, yep, good catch. Good catch. I was like, why isn't this working? So look, so this is 14.5 KSI, so pounds per inch squared, right? So here, up here at the top, we have foot times pound. So we need to convert that. There's 12 inches in 1 foot. Okay? Now let's do it. There we go. 0.429 inches. So again, this is the radius. So in order to find the diameter, you just multiply by 2, right? 2 times r. So you get 0.858 inches, which, let's just make sure we can pick a size. So it'd be 7/8 inch. Okay, so slightly bigger, which would work based on our allowable shear stress. Okay, so here's a few examples of torque, of using power, and I hope it is a good review, but also will help with your machine design homework. Thank you.